So having earlier seen how to calculate the average atomic mass using abundances, what we are now do is reverse engineer the abundances for particular isotopes if I know the average AR. So we'll look at some examples where we'll be given isotopes and the average mass, and we'll be asked to find the abundances of each isotope. The only way to show how this works is I'll have to do some actual examples. So let's see the first one. This one, also given in your notes, is naturally occurring potassium consists of potassium 39 and potassium 41. So they're saying that we have potassium, which is K, the element. So one isotope is potassium 39, and they're saying one isotope is potassium 41. And they're saying that knowing that the AR of potassium is 39.1, what is the abundance of each isotope? Let's say you don't know the abundance of any of them. What you do know is that the total of percentage abundance in term relative percentage abundance would have to equal to 100. So if potassium 39 has an abundance of X percent, potassium 41 would have it 100 minus X percent. That's what we know, because the total has to be 100. So the way this works out is that if you want to find the AR, which is the weighted mean, you take the mass of 39 into its frequency, which is abundance, and the mass of 41, that's that isotope, into its abundance, which is 100 minus X. And in this case, you could have taken this X and this 100 minus X, or vice versa. You'll get the same value for either isotope, each of them. So this is basically over what? So this is over total abundance, which is X plus 100 minus X, which is actually X. And this equals to 39.1. So all of this equals to 39.1. So when you solve for X here, you'll get the answer. And if I solve this, X would actually come out to 95%, 95, which means that the abundance of potassium 39 is 95%, and the abundance of potassium 41 is only 5%. And that in fact will be the abundances for each of them if you take them into account, and you'll get this AR, by the way. All right.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
Let's take a look at another example. Here it says here that the relative atomic mass of copper is 63.5, and the relative abundance of the two copper isotopes are 63 and 65. So when you don't know the abundance of any of the two isotopes, generally it only works for elements that have only two isotopes. So it's copper 63 and copper 65, and let's call this X, and this will therefore be 100 minus X in terms of abundance. And how does one solve this? Well, the AR would be, which is the mean value, weighted mean, 63 times X. So let's take that as 63 times X plus the other fellow is 65 times 100 minus X, and the total is over 100, and this equals to the AR, which is 63.5. In fact, here the value for X will come out to 75. So this value is 75 and this is 25%. Now this is 75% and that is 25%. All right. Now obviously you took X as the abundance of copper 65. If you had taken this to be X and this to be 100 minus X, then your X would come out to be 25, which will still make this 25 and this 75. So either of them is X and the other one is 100 minus X, and you solve for X and you'll get the abundances for either of the two isotopes. Yeah. Now in this case we've got two different isotopes of gallium, which are 69 and 71. But what's different about this is that their isotopic masses are given more accurate than just mass numbers. So even though it's 69 and 71, the isotopic mass for each of them is, like the left one is 68 point, so that's the mass is 68.9 70.93, and the mass of gallium-71 is 70.92. Yeah, and you're about to find the abundances, so you give any of them as x and the other is 100 minus x, and total percentage is 100. At that stage you'll realize that the relative atomic mass of gallium is 69.72. So the method is that the AR, which is 69.72, is basically when 68.93 times x happens plus you have 70.92 into 100 minus x, all of that over 100, because that's the average. Total abundance is 100%. That equals to 69.72. And then you solve for x by multiplying, so the yellow part becomes 68.93x plus, so 70.92 times 100, which gives you 7092 minus 70.92x is equal to 100 into this 69.972, which is 6972. And just simplify. So now simplify, I can take basically take this number this side and take both. I mean, or you just add them up first. So 68.93 minus 70.92. So that's minus 1.99. So what do I have is 70.92 minus 1.99x equals to 6972. And so take this fellow that side or that fellow that side. Either way, it doesn't really matter. You know the algebra from here. So what do I get? I get minus 199x equals to 6972 minus 7092. That becomes minus 120, 1.99x. And so what you get, x is as 60.30%. So let's just write that, 60.30%. Therefore, the other fellow, which we have right here. So this is 60.30, and therefore this is 39.70, because 100 minus 60 is 0.30 is 79 is 39.70. Let me write that down. So like I was saying, this, if this is 60.30%, this is 39.70%, and that's the two abundances for the two isotopes of gallium. All right.
Hey there! If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?